and so we'll test it on the test rows. And so just a standard first step, I ran a linear regression. And so I kind of declared a model here with certain parameters, like the prediction column will be this PIC50, and then I fit it on the training data. And so that is all saved in this LR object. Um, and what you can do then is then evaluate this model on a test data set. And so, I printed it out here, and you can see that the root mean squared error is 1021. Um, this and so the range of the rectal range of this y value PIC50 is between like 0 and 10 or 0 and 9. And so this is telling you that this model is doing pretty poorly. Um, Another way to kind of generate predictions is actually using LR transform. And so taking the model and transforming it on the testing data, and this will generate a new data frame called LR model. And so LR model is kind of interesting. Let's see if I have it here. Yeah, so LR model is a data frame that has all the original columns of um, DF scaled, except it adds one more column called prediction. And so you can select these columns and just do a rundown and compare them just to see what it looks like. And we'll do kind of some visualization later to look at it more closely. Um, so one thing that I had in mind was that because we have so many features relative to the number of rows, we have um, you know 900 features and only maybe 1,200 observations. It's quite likely that we're going to overfit. So one of the things I wanted to do was try ElasticNet and see if we could regularize this model. And so, same linear, still regression, but now I'm going to do a grid search to do hyperparameter tuning for ElasticNet. And so, two main parameters, the regularization parameter, which is lambda, and so that's just the kind of coefficient on the penalty. And then ElasticNet param is the balance between the L1 versus L2 norm. And so this is just going to do a grid search between these hyperparameters. Here we're establishing an evaluator. This evaluator is basically just going to spit out a metric, which we can specify, which is the root mean squared error. And so we're going to do cross-validation and then fit it on the training data. And then it's a little bit difficult to get out all the hyperparameters, and so I'm just going to focus on the best model. And then you can evaluate the best model and see how that performs. And you can see it does it much better, but it's still really bad. And we'll see why in a second. So yeah, what we're going to do next is to visualize this data just to see what is going on. You typically have to convert. I think the only way to do that is really to convert to pandas. And so I'm just taking these models, selecting the columns we're interested in, and then converting them to pandas data frames. Yeah, this is just to rename the columns so that you don't get duplicate columns. Merging the two data sets, the two models into one data frame so we can plot them together more easily. And then here, this is just plotting in Seaborn the predicted values versus, so these are the predicted values from the model, and then these are the actual values. And so ideally it'd be straight line, but as you can see here, so this is linear regression, this is ElasticNet. I think it's a little bit, y value is a little bit compressed, but this is the linear regression, this is the ElasticNet. You can see that the predictions are just way off. It's below 0. So you can see that there's like some serious outliers here, 3 outliers, and we can identify that pretty easily by looking for where the error is and returning the index. You can see that there's 3 main outliers here, and potentially we can refit the model with the outliers drop. But potentially what this also means is that there's a non-linear relationship with the features, and so we can look at all kinds. And so you could potentially explore non-linear models as a way to better fit the data set. And so there's a lot of non-linear approaches. One that I looked at was gradient boosted trees. So these Also can be easily trained in PySpark. And so this is just the same thing as linear regression, but in terms of defining the model, but just obviously using the gradient boosted tree regressor. And then I fit that model on both data sets, the training data set as well as the training with the expanded feature set from Multivec. Um, and you can see that the root mean squared error is much, much lower. Um, but I would say on an absolute scale, like that's still kind of high. Um, and yeah, so this is just training the model again, generating predictions, and then we can evaluate those predictions using the evaluator that we talked about earlier, um, and then we can print those out. So yeah, these are the root mean squared errors for those two models. And of course, we can do hyperparameter tuning to kind of fine tune those as well. Again, we're just to do some visualization to see the performance of these, to look maybe at any outliers and potentially identify why they're outliers. Maybe certain chemical substructures or something interesting about those outliers that we can try to um, address. I'm just converting to pandas data frames again, and then visualizing them. And then what you can see here with these two models is that they do a much better job, obviously, than the linear models, but potentially there's a lot of room for improvement. And so it'd be interesting to try, convolutional neural networks, graph, models, um, and so that is something that we can do in the future. Thank you.